Suppose I have a game board and I start in the middle, where this heart is, and then the rules of my game are I roll a 4-sided die, I roll it many times. If I roll a 1, I go north. If I roll a 2, I go east. If I roll a 3, I go south. If I roll a 4, I go west. These are the rules. Let's see how it works. I roll a 3, so I go south. I roll a 1 next, which brings me back north. Next I've rolled a 1, I go north again, then a 4, I go west. A 1, I go north. A 2, I go east. Another 2, east. Another 2, east. Another 1, north. Another 2, east. This is a 10-step random walk. This topic of random walks is surprisingly useful in physics. Much of what we like about physics is that it allows us to predict behaviors in systems using Newton's laws, but sometimes systems are complex enough that we can model them with different techniques, such as the random walking of particles. Let's look at another example. Here is a hexagonal grid representing the surface of silver, a block of silver, and we see one silver atom taking a random walk on the hexagonal grid. Here the color is indicating how often the atom has revisited that site. So the yellow are places that the atom has visited often. The black and red are places not visited often. The black is only one stay at each location. So we can have different grids that allow us to take random walks. We can even have a random walk with no grid. Suppose I look at gases, the motion of the atoms in the gas, resulting collisions. Those collisions cause the particles to change their direction. They take many steps. Those steps are mediated by collisions that change the direction. This is a simulation made by Wikipedia contributor Lukang. From the same contributor, we can see a random walk of a large particle, like a piece of dust, floating in gas, and the gas hits the dust with random collisions that cause the random walk to occur with this dust particle, which is being tracked here. And this is what was described long ago, most famously by Brown, what we call Brownian motion, the motion of pollen grains in water due to random motion of the molecules. It's part of the evidence we have for molecules, early evidence. So how does this interest us in our study of thermal physics? You know, we have the hot reservoir and the cool reservoir, so we have collisions between molecules in these two parts of the engine. And motion of the gas through this system, expansion and contraction, causes it to operate the engine. So we have a connection here. We have the hot reservoir and the cold reservoir, and different momenta of particles in the hot and cold. We'll of course be having random walks of particles throughout this, and we'd like to describe the motion of the gas and the motion of the atoms in more detail by taking a look at this random walk idea. Suppose we have a one-dimensional random walk. We could roll coins, and if I roll a head, I step right. If I roll a tail, I step left. And this table is showing all of the places I can end up with 5 rolls. You can see this becomes rapidly more complicated as I've rolled even just 5 flips of a single coin. Of course it's more complicated in 2 dimensions, but some questions we could ask would be, how many different lengths can a walk of n steps be? How far do I end up traveling after n steps? How does that distance depend on the dimension of the walk? If I walk on a 2-dimensional grid like my first example, or a 1-dimensional walk, or a 3-dimensional walk, how do these answers change? How many different points can a walk of n steps lead to? Or how many different walks can lead to the same endpoint? What's the average displacement of an n-step random walk? If I take 1,000 walks of 100 steps, how far do I travel on average if I average those walks? I might also have more directly physics-related questions, like what kinds of physical objects can random walks build or simulate, and how do random walks relate to thermal systems behaviors, like Brownian motion and diffusion? We'll talk about these topics in the following videos.